Hi, thank you for joining me. I'm Yaniv, and today I want to tell you about how people guide their learning in an uncertain environment when they get no immediate reward, but they do have to use their memory in order to explore. And we ask what computation underlies choosing potential learning experiences in such a situation, and specifically, how is that computation may be implemented by the human cognitive system, which has severe capacity limitations. Without further ado, I'll introduce you to our paradigm. Our participants are spending their time in a virtual room with 4 tables. Each table has 2 decks of cards in it, and if you flip a card on one of these decks, it may be blue or it could be orange. Now, in each table, one deck of cards always has more orange cards in it than the other, and obviously the other one has more blue cards in it than the first. Participants' job is to learn the differences in proportions of color between the 2 decks on each table. They do so by first exploring and sampling cards, and then in a later phase, they are tested on their knowledge. So in the exploration phase, they are presented with 2 tables which they can choose to explore. They choose which to explore, and then they get to choose a card deck to sample a card from. This goes on for a random number of trials, and our participant knows that at any given moment, the exploration phase may end and they would be tested on their knowledge. At test, we tell them that one of the colors, for example, the orange, is worth extra money. Then we take them to each of the tables where they have to indicate the deck of cards with more orange in it. If they make a correct choice, they get a bonus. Crucially, they are only rewarded for test phase performance. So during exploration, they are free to maximize their learning rather than to trade it off with reward. How would you choose which table to explore in this game? We took a rational analysis approach and derived the optimal strategy, which is to maximize information gain. Information gain is the difference between the uncertainty of your knowledge right now and your future uncertainty after observing the next card. Now, this future uncertainty may be difficult to compute because it involves taking an average over cards unseen yet. So an easy simplification is to just go by your uncertainty, choose the table that you're most uncertain about or that you know the least about. That makes sense, but could still be too difficult because it involves computing uncertainties. So maybe participants are doing something really simple and are just equating their previous exposure or equating their visitations between tables. So choose the table that you visited the least number of times in the past. So now we have 3 hypotheses, and we may ask which best predicts human choices. So today we're going to look at the performance of 65 MTech participants, each completing more than 1,000 trials of this task. And we actually took the true trial sequence that each participant observed, and we showed that to an ideal Bayesian observer who formed beliefs about the proportion of colors in each deck on each table. From those beliefs, we derived our 3 behavioral predictors: information gain, uncertainty, and exposure. And we saw how those may explain choices and reaction times. So how did they explain choices of tables? If we look at uncertainty, what matters is relative uncertainty, the difference between the uncertainty for the table on the right and the one on the left, in order to choose between them. And we want to see how that, plotted on the x-axis, explains the proportion of actual right table choices. If uncertainty is the strategy participants are using, we expect a positive relationship here. And indeed, that is what we see. How about the optimal strategy, information gain? If that is what participants are doing, we expect a positive relationship here as well, and we don't quite see one. So maybe participants are doing something really simple, going by exposure. Again, we expect a positive relationship here, but we see a weirdly shaped negative one. I'm happy to talk about that on Discord if you find that interesting. Using formal model comparison, we see that indeed, the uncertainty of the current knowledge is the best predictor of choices. And it's not only a predictor of choices, as we see in this graph replotted here, but also of reaction times. If we plot uncertainty versus reaction times, we see this inverse U shape, indicating that indeed this may be the decision variable that the participants are using. So we have a handle on what computation, but how is that implemented? So we may ask if the choice strategy is modulated, but how difficult it is to compute the decision variable. That will give us an idea about capacity limitations and how they modulate strategy. And we can hypothesize 2 things. One is the noise hypothesis, that exploration becomes more random when things are difficult to compute. Alternatively, we could see resource rationality, where participants are systematically adapting their strategy when things are difficult to compute. So what is our handle on computational difficulty? If you have 2 tables and you have uncertainties, the difference in uncertainty we saw is our decision variable. But the sum of uncertainty or total uncertainty is regarded in the literature as a measure of computational difficulty. And indeed, if you plot total uncertainty against reaction times, you see that they rise monotonically with it, indicating that making choices is more difficult when total uncertainty is high. Now, how is choice modulated by total uncertainty? I'm plotting total uncertainty on the x-axis, and on the y-axis, I'm plotting the influence of our decision variable, relative uncertainty. What we would expect is a flat positive line here, indicating that always participants are choosing the table that they are most uncertain about. We see that, but only for low and medium total uncertainty. For high total uncertainty, we see a strong negative relationship. Let's break that apart. When we look at the low total uncertainty regime, we see the positive relationship between relative uncertainty and choice that we expect and know by now. But that changes into a flat one as total uncertainty rises. And with high total uncertainty, we see a strong negative relationship, indicating that participants are choosing the table that they are least uncertain about. Now, that is not noise. That is a systematic modulation of strategy. But choosing the table that you're least uncertain about amounts to reducing the rate of information intake. Why are participants doing that when total uncertainty is high? Perhaps they're doing it in order to reduce load when it is difficult to compute a decision variable. But you may ask if that is a suboptimal thing to do. They are reducing the rate of information intake. In order to answer that, we leverage individual differences. On the x-axis, we plot how well this combined strategy explains participants' choices in the exploration phase. And on the y-axis, how well participants do at test, a measure of their total learning. We see a positive relationship here, indicating that participants who deviate from this combined strategy do less well at test. So at the very least, regulating information rate in this way is not suboptimal and perhaps resource rational. To summarize, I showed you that we can measure exploration in a stochastic environment with memory load, which is a novelty in the literature. Overall, participants explore the objects that they know the least about. But this strategy is strongly modulated by computational difficulty, with people switching between avoiding and approaching uncertainty. I want to thank you for joining today. Thank my advisors, Daphne Shohami and Michael Shadland, and the Shohami Lab. And I'm looking forward to seeing you on Discord.